Okay, so section 2.3, we're talking about measures of spread, and if you remember, we were thinking about picturing a set of data as a bunch of points on the number line. And the idea here is, I don't know if you watched one of the previous videos, but the idea is if you imagine all the points on the number line, each piece of data is like a little LED light lit up on the number line somewhere. The question is, how spread out are those pieces of data? Are they all bunched up close together? Are they all spread out? And can we measure that in some sort of way? So that's the point of measures of spread, or measures of dispersion, if you want to sound a bit cleverer, with a multi-syllable word. So the range, largest take away the smallest, straightforward. Interquartile range, the upper quartile take away the lower quartile, and then we can do interpercentile ranges if you split the data up into percentiles. There's nothing that I can add to that bit other than what's in the book already, I think, and then there are some questions they can ask you on that. But it's a mixture of read the information in the textbook and make sure you know your GCSE interquartile range material. Now, variance and standard deviation, this is where it gets a little bit more interesting. The range would be the distance between that piece of data and this piece of data. The interquartile range might be the difference between this piece of data and this piece of data, say on the number line. So if you imagine all the number line with all these bits of data dotted around on it, they're fairly crude measures of spread, aren't they? What if I have a number line that looks like this? I've got lots of data all together there, and then a couple of bits over here, and then a lot of data over here maybe, and then a few more bits over here. If I'm just taking a very rough measure of spread with the interquartile range or the range, it's not sort of taking account of those things. So what we'd like really would be a measure of spread that takes account of all the pieces of data. So that's what we get in variance and standard deviation. And this is how it works. So if we've got all our data on a number line, and let's say the average, the mean is there, somewhere in the middle, and then there's lots of data all spread out around it, okay? So what I'm really interested in is how far away from the mean is each piece of data. So these little pieces of data, remember, we give those the letter X, and I could look at this measure, X take away X bar. So for this piece of data, that would be this distance here. For this piece of data, that would be this distance here. So I'm measuring how far away is each individual piece of data from the mean. And if I took an average of those distances, then that might give me a nice measure of spread, wouldn't it? You know, the average distance away from the mean. With the variance, that's essentially what we try and do, but we spot this problem. We spot that if I do X take away X bar, for any of these pieces of data down here, that's going to end up with a negative answer because they're below the mean, they're lower than the mean. So if I do this number take away this number, I'm going to end up with a negative answer. So if I do X take away X bar and find the total of all those distances and then try and divide by n, if I try and find the average of those distances, some of them are going to be positive, some of them are going to be negative, and we're not going to get the measure that we want. But if we square them all, then the small distances, when I square them, will come out small. The big distances, when I square them, will come out big. But crucially, the negative distances, when I square them, will come out positive. So a small negative distance turns into a positive number when I square it. Now that might seem a bit funny. Why not just take the distance and ignore the symbol on it? So if it's negative, just turn it into a positive number. Well, this is the way that we've chosen to do it because later on, when we look at the rest of the maths, this is the one that kind of fits in nicely. So we're going to find those things, and we're going to take the average. So add up those measurements and then square them. So the idea with variance is that we want a measure of spread which relies on some information from all the bits of data. The way we're going to choose to measure it is think about the distance of each piece of data away from the mean. We can't just do X take away X bar because sometimes that's going to be negative. So we do X take away X bar and square it. And then we find the average of those distances. So add them up and divide by how many there are. So it's the mean square distance from the mean is another way of saying variance. So find the distance from the mean and square it. That's the square distance from the mean. And it's the mean of those things. So add them up and divide by how many there are. I hope that sentence makes sense. It's the mean of the squared distances from the mean. Now, that's the definition of variance, and that's one of the formulas for variance. But we can see in the textbook, and hopefully you'll be familiar with already, that we have another one. And the point of this one is that it's easier to calculate. So sigma x squared over n minus sigma x over n all squared. So let's just look at this formula. Sigma x squared means take all the data and square it, then add it up. Now that's pretty easy to do if you've got a table. Take all the bits of data in the table, square them all, add them up, and then divide by n, okay? This over here, well, sigma x over n, that's the mean, isn't it? So this is the mean of the squares, take away the mean squared, is how some people would say that formula, okay? So sigma x over n, that's just our, same as x bar, that's our mean, and we square that. So find the mean first of all and square it, then square all the bits of data, and add them up and divide by how many there are. There's one more formula sitting here in the textbook, which is this one here. It's just helpful to have a bit of notation for this bit, the total of the square differences from the mean, so just the top bit of the formula, because we tend to use this, this comes up elsewhere as well. So we'll just introduce that notation there, and you can see that it's basically variance times by n, isn't it? So it's perhaps possible to see from this formula and this formula how times by n, and that n there will disappear. This should be an n squared, so it just turns into an n when I've times by n. So sort of helpful, but this line, you could probably ignore this if it weren't for the fact that sometimes they may mention that explicitly in exam questions. You could ignore that and just stick to these formulae. This one here, that's the one that we'll use most often traditionally in exam questions at A-level. That's the one that gets most often used. This one here is because that's where the definition of it comes from, and maybe they could ask you to do that specifically. Maybe they could somehow ask you to use that formula. But as a rule, that's the formula that we'll use. And that is exactly the same as this thing. And why introduce this extra notation of SXX? Well, just because later on we tend to use that as part of different formulas as well. So the exam board have chosen to introduce it now. Now, that's our measure of spread, that's our variance, but there's a problem with variance, and it's this. If all my data is, for example, a length, then what units does the variance have? Well, if you think about it, if I do x minus x bar, well, first of all, if all the data is a length, then x bar is going to be a length, isn't it? If for example, the data I'm measuring is everybody's height, then the data is all lengths, and the average height would also be a length. Fine. Then I do the piece of data, take away the height, that's still a length, isn't it? So this measurement here is a length. Now, when I do a length and I square it, what I get there is an area, isn't it? So when I add up all the areas, I've still got an area, and then I divide by a number, I've still got an area. If I take an area and divide by 6, I've still got an area. So if the units for all the data are in centimetres, the variance is measured in centimetres squared. And there's something wrong with that, isn't there? I can't say, oh, here, I've got all this data, it's an average of 10 centimetres and a spread of 5 centimetres squared. That doesn't really make sense. So what we're going to do is we're going to take the variance and we're going to square root it to compensate for these funny units. And you can sort of see the square root, we squared somewhere in the formula, so if we square root at the end, that's sort of fair enough, isn't it? They don't cancel each other out because we square here and then add all those bits of data up, but they sort of balance each other out, morally speaking, if that makes any sense. So we don't use the variance as a measure of spread because the units are in a bit of a mess. We square root it, and when we square root an area, we get a length. So we are back in the units that we started with. So notation-wise, sigma, lowercase sigma written like that is our standard deviation. Sigma squared is our notation for the variance. And standard deviation is the measurement of spread, which we will use most often. We're nearly there with measures of spread. Just one more thing to mention is these formulas at the bottom of the page here. And this is when we're using a frequency table. Now, if we look at these formulas, they are the same as the formulas at the top of the page, but we're using frequencies as well. So if you think about this, x minus x bar squared, and then sigma, so add all of those up. So for every piece of data, do the piece of data, take away x bar, square it, and then add that onto the next one. Now, if you've got 3 pieces of data, which are all 35, which we have over here in our first example, we've got 3 pieces of data, all of those are 35. You could do 35, take away the mean, square it, 35, take away the mean, square it, 35, take away the mean, square it, and add them all up. Or you could just do that once and then times by 3, couldn't you? So in other words, you could do frequency of each piece of data times by that piece of data, take away the mean, and then square it. So we can stick a frequency in the formula. If you think about what frequency means, if you think about what the formula means, hopefully that'll make sense. N from our top formula here is the same as the total of the frequency, and then that follows through into the rest of the formulae. Now, when it comes to revising this, it's helpful to know where these things come from. It's helpful to know where this comes from. You'll notice I've not told you how to get from this formula to this specifically. You can get from that to that with a bit of tricky algebra, and you can sort that one out. I'm not going to go through that at the moment because it's not hugely important for this particular exam. But this is just a rearranged version of this. Now, when it comes to the exams, you need to memorize these formulae, you need to memorize these formulae, and particularly that one is the most useful up there, and this one is the most useful down here. Make sure you know them all, but those are the ones that you'll use the most often.